Okay, thank you very much for attending this meeting. And my name is Yuanzheng Wen, and currently I'm a undergraduate researcher at the International Research Center for Planetary Sciences. And I will also become a PhD student at the University of Iowa very soon. And my topic here today is about the statistical study of the IMF flow aligning component impact on the currency structure in Martian magnetotail. And first of all, I'd like to thank all my collaborators for their great contribution as work. Thank you very much. And here's my email website, and please feel free to contact me if you have any question about the presentation. So here's the outline of my work. First, I want to introduce the background and motivation of our work. Then I will talk about the details of our work, mostly including the method, results, and conclusion. And then we'll move on to the Q&A section. In background, the space environment of Earth and Mars is very different, as Earth has a global intrinsic magnetic field, while Mars does not. However, the solar wind can interact directly with Mars' upper atmosphere, and the IMF will drip around Mars, thus forming the unique induced magnetosphere of Mars. There are many interesting characters regarding the induced magnetosphere of Mars. We will mainly focus on the magnetotail here today. So the stretching and dripping of the IMF forms a magnetotail with two lobes of opposite polarity and separated by the current sheet. Here the right diagram shows the magnetic lobes in the magnetotail. The blue contour represents the tailward magnetic field, and the red contour represents the sunward magnetic field. So we can sum up some interesting characters of the magnetotail of Mars. The magnetotail consists of two magnetic lobes, one directed towards Mars, one directed away from Mars, and the current sheet is in the middle of the two magnetic lobes, and it's also known as the plasma sheet. Well, in ideal situations, the magnetic field structures in the tail would be symmetric, and the size of the two magnetic lobes should be equal, and the current sheet should lie between the two magnetic lobes perfectly. However, the magnetic field structures in the tail would actually be influenced by many factors. One of the factors is the crustal magnetic fields. It is known that Mars has a very strong crustal magnetic fields in the southern hemisphere, and the crustal magnetic fields can actually influence the space environment of Mars significantly. A study by Genetic Laboratory in 2018 and 2022 found the twist structure in a Mars magnetotail based on both wavelength observations and image simulation. And it turned out the twist structure is actually caused by the crustal magnetic fields. And the physical mechanism behind it is the magnetic reconnection between the crustal magnetic fields and the interplanetary magnetic fields. So we can tell that the crustal magnetic fields can influence the tail of Mars. However, today we'll mainly focus on the influences from the IMF. Our motivation comes from a very early study by Dave Mike Thomas in 1986. They used the data from Pioneer Venus Orbiter. It seems like they found that the IMF flow align component can influence the magnetic tail structure of Venus by causing an asymmetric magnetic field structure. However, a study by George Rong in 2016, they used the Venus Express data. However, they found the IMF could not influence the magnetic tail structure of Venus significantly. So their results seems to be inconsistent. So today we changed the object of study by looking at Mars to study whether the IMF flow aligning component can influence the magnetic tail of Mars. So we can know the influences of IMF on unmagnetized solar system bodies. So we use the data from MAVEN because MAVEN can process sample different regions of Martian atmosphere and the magnetosphere, and observations of the solar wind can help us monitor upstream solar parameters and solar activity. So in order to study them, how the magnetotail responds to changes in solar wind and IMF, we look for orbits where MAVEN can measure both the upstream solar wind and the magnetotail. So first, we select the MAVEN magnetosphere crossings under steady RMF conditions. We first select the MAVEN magnetosphere crossings from October 2014 to February 2020, and there are more than 7,000 crossings. Then we set up the steady RMF criteria, mostly two criteria. First, we want the deviation angle between B1 and B2 is less than 30 degrees, and B1 and B2 represents the averaged RMF 30 minutes before and after the boson crossings. And we also set up the strengthening criteria. And based on these two criteria, we have selected more than 1,000 magnetosphere crossings from MAVEN. And here's an example of the magnetosphere crossing from MAVEN. It can measure both the upstream solar wind and the magnetotail. Then we selected current sheet crossing cases based on MAVEN data. And the current sheet crossing is mostly identified by the reverse of the BX component in the magnetic field data and the enhancement of the electron fluxes and ion fluxes. So it's a very beautiful current sheet crossing in the magnetotail. And here's another one, current sheet crossing cases. And we have selected the current sheet crossing cases in the magnetotail based on some criteria. First, we do not want to see flapping events in a current sheet during the crossing, and the current sheet crossing should occur only once during the magnetotail crossing. And we also use the same steady RMF criteria, and also we do not want to see large fluctuations in upstream RMF. And to avoid potential influence from the coastal magnetic fields, we want the MAVEN to be flying about 400 kilometers when it's flying over the coastal magnetic field region. And we applied the MVA method to the current sheet crossing cases we have selected. I won't spend too much time talking about the details of the minimum variance analysis, as it is a very well-known method in space physics, mostly based on the Maxwellian boundary conditions. And by applying the MVA method, we can get the normal direction of the current sheet, which can help us with further analysis. And to study the RMF influences, we want to quantitatively analyze the displacement of the current sheet in the magnetotail. We hope to calculate the shift of the current sheet, and the diagram shows how we're going to do that. The bold black line represents the ideal current sheet location, and the dashed black line represents the current sheet crossing observed by MAVEN. N is the normal direction of the current sheet derived from the MVA method. And we can get the deviation angle alpha and the shifted distance delta d with this equation, along with the angular uncertainty. And here we define the displacement to be positive if the current sheet is moving towards the minus bx side, and the displacement to be negative while it's moving towards the positive bx side. And we have actually calculated more than 14 cases based on some previous criteria. And here we get the correlation between the current sheet shift distance and the RMF cone angle. The left diagram shows the meaning of the RMF cone angle. It actually shows the significance of the RMF flow align components. The RMF is sunward or tailward if the cone angle is near 0 or 180 degrees, and the RMF is cross-flowed if the angle is near 90 degrees. And there's a beautiful inverse correlation between the RMF cone angle and the current sheet shift distance. And the current sheet would move to the positive side if the cone angle is near 0 degree, and while the RMF, and it move to the negative side if the RMF is near 180 degree, while the current sheet would be stable in the middle of the two magnetic lobes if the RMF cone angle is near 90 degree. And to make the results more convincing, we also conducted a statistical study of the current sheet structure in the tail using MAVEN data from October 2014 to February 2020. The work is conducted in MSU coordinates. Z-axis represents the x in ms coordinates, and z-axis represents the direction of the motional electric field, and the right axis completes the right-hand rule. And the axis is basically contained in the Cauchy plane, which is normally located at y ms near 0. And we selected orbits that meet the IMF requirements, and we set up ms coordinates using upstream steady IMF conditions. And then we transform the magnetic field data into MSU coordinates. And we divide the IMF Cohen angle into 3 categories to represent different IMF conditions. Then we compute the contour of the BX equals 0 to represent the configuration of the Cauchy structure in the magnetotail. And then we get the statistical picture of the Cauchy structure in the magnetotail under different IMF conditions. When IMF is sunward or tailward, the magnetic field structures will be asymmetric, and the Cauchy will be shifted to the negative side, the positive side, and negative side. If the IMF is cross-flow, the magnetic field structures will be symmetric, and the Cauchy will lie between the 2 magnetic lobes. And this is consistent with the correlation we have shown before. The upper panel shows direct measurement from MAVEN, while the lower panel excludes magnetic field measurement when MAVEN is flying over the crustal magnetic field region in the tail. So we cannot see much differences in the picture caused by the crustal magnetic fields, and the IMF seems to be the controlling factor. And here, again, we should a zoomed-in picture of the Cauchy structure. We can tell that the IMF is still the controlling factor to cause the asymmetric structures in the magnetotail. Then we move on to the conclusion. And it seems like there's a systematic asymmetry in the location of the Martian magnetotail Cauchy in a modified MSU coordinates. And the shift distance of the Cauchy is very sensitive to the IMF cone angle. And the asymmetric is mostly controlled by the IMF flow line component. And also, we see some other influences. And for the future work we wanted to do, we want to analyze on the atmospheric effects on the Cauchy effect. There's a very early study by Michael Lemon. They showed that the solar UV intensity can also influence the Cauchy structure and cause the displacement of the Cauchy. And so we want to quantitatively analyze the solar UV intensity effects on Cauchy and compare with the simulation work by Lemon and other works which we're trying to come up with more. And thank you very much for your attention, and I'll be very happy to answer any question now. Thank you.